Today also we have valence bond theory, but it is for 4 coordinated complexes. 4 coordinated complexes. Example, NiCO4. Here coordination number of nickel is 4. As we have seen, in the case of 6 coordinated complex, you just write the configuration of nickel, that is 3D8, 4s2 and 4p0, 3d5 and 3d8, 4s2. But here carbon monoxide is neutral, so charge of nickel is 0. Oxidation number of nickel is 0. So again you just write nickel, not ion. In previous video we had ion here. Again you just draw the D8 4s2. But the carbon monoxide ligand is the strongest ligand in spectrochemical series. So internal pairing is sure. So this electron pair up to this orbital and this electron to this orbital. So you can draw it like this. (3d10). So 4s is vacant and 4p is already vacant. Now you have to check the coordination number, that is 4. So 4 orbitals are required for hybridization. They are 1s and 3p. Hybridization is fixed, that is sp3. sp3 hybridization can be seen. So the metal unhybridized orbital can be given like this. Thereafter you have 4 orbitals which are hybridized. To that hybridized orbital you will get nickel except lone pair from carbon monoxide. How many carbon monoxide? 4. They can put like this. sp3. For sp3, what shape we can expect? That is tetrahedral shape. So here you don't want to say whether it is outer or inner. That kind of any classification is possible here because d orbitals are not involved in hybridization. This is 4 coordinated system. D orbitals can participate only in hexacoordinated system, but is possible in 4 coordinated system of square planar shape. But it is tetrahedral, so there is no chance of d orbital. So shape is nickel and tetrahedral shape, CO, CO, CO and CO. This is the shape of tetracarbonyl nickel. Next one is again 4 coordinated system, that is NiCl 4 2 minus. You draw nickel configuration 3d 8 4s2 and 4p0, 3d 8 4s2. Here nickel is not in atomic state, in ionic state. Oxidation number of nickel is +2. You calculate the oxidation number of nickel, you will get it is +2. So you remove these 2 electrons. So the remaining is 3d8 only. 4s is now vacant. 4p is already vacant. Now you think how many orbitals can be sent for hybridization, which is equivalent to coordination number, that is 4. So 4 orbitals can be sent for hybridization. So before going to hybridization you have to check whether any chance of internal pairing. Here there is no chance of internal pairing since Cl minus is a weak ligand. Cl minus is a weak ligand, so internal pairing is not possible. So these electrons will remain as such. These 4 orbitals undergo hybridization, 1s and 3p. So hybridization is sp3. sp3 hybridized. So what to get? Nickel 2 plus in presence of Cl minus, which is a weak ligand. Configuration is like this, and now you will get electrons from Cl minus, lone pair from Cl minus, and shape is again tetrahedral, as the hybridization is sp3, shape is tetrahedral. You just draw nickel, Cl, 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 and 4 minus, 2 minus. This is the shape of tetrachloronickelate 2 ion. Again you have one more species, that is NiCO. NiCN 4 times 2 minus. Here cyanide is a strong field ligand. As usual, you just draw nickel 3d8, 4s2, 4p0. Here also nickel is in +2 oxidation state, so remove these 2. Thereafter you have like this. But nickel 2 plus, when approached by Cn minus, which is a strong ligand, internal pairing is possible. So configuration pair, this is again pair, this is also pair. Thereafter this electron pair to the inner d, and this orbital become vacant. Now 4 orbitals can be sent for hybridization. They are 1d, 1s and 2p. So hybridization is dsp2. So the hybridized orbital can be drawn like this: 2, these 2, these 2, and these 2. So hybridization is 4 orbitals. They were 1, 2, 3, 4. They can accept lone pair from Cn minus. Lone pair you have to draw in cross mark. So hybridization is dsp2. So shape is square planar. Here inner d orbital is involved in hybridization. For that reason, you don't want to say it is inner d complex. For square planar complex, you have only one hybridization, that is dsp2. But for octahedral complex, you have 2 hybridization, sp3d2 and d2 sp3. So that you have to mention whether it is inner d or outer d. But here there is no confusion. Here you have only one possibility of hybridization, that is dsp2. There is no choice of sp2d. So you don't want to say it is an inner d complex. You just draw the shape. Since hybridization is dsp2, shape is square planar. What is the shape? Square planar. Square planar. Just draw a square. You put nickel at the center and 4 cyanide, Cn, Cn, Cn and Cn. Now total charge is 2 minus. This is the structure of tetracyanonickelate 2 ion. These 3 are 4 coordinated complexes. So we are coming to the end of the valence bond theory. Now we have to see what are the merits and demerits of this theory. Merits. Valence bond theory is more advanced than Werner's theory in explaining the concept of bonding and nature of bonding, and it is able to explain successfully the structure and magnetic properties to some extent. Then demerits of valence bond theory. Even if it has some merits, large number of demerits have been reported. Valence bond theory assumes a rather qualitative approach of bonding. It does not account the bond strength and bond energy like any quantitative parameters. It gives only qualitative explanation. And spectra of complexes are important in coordination chemistry. That spectra could not be explained by valence bond theory. And it has no idea about the quantitative aspect of magnetic moment of complex. Magnetic moment of complex can be calculated from valence bond theory using the number of unpaired electrons, using the equation root of n into n plus 2 Bohr magneton, where n is the number of unpaired electrons. But this calculated value will not be same as the experimental value. So this discrepancy could not be explained by the valence bond theory. And it is silent on the relative rate of reaction, how complexes react and what is the rate of the reaction. That kind of kinetic parameters are not explained by this theory, and it could not explain the mechanism of reaction also, and it is unable to explain why Fe3 plus form tetrahedral as well as octahedral complex, why Fe3 plus can form outer D complex at some times and inner D complex at other times, but chromium 3 always form octahedral complex only. Chromium does not have any tetrahedral complex. This kind of parameters could not be explained by valence bond theory. And temperature dependent paramagnetism is an important parameter for complexes, but this theory failed to explain that temperature dependent paramagnetism, and it failed to take into account the orbital contribution to magnetic moment. These are the major drawbacks of valence bond theory. In order to overcome limitations of this theory, we have some other theories also with us that we can discuss in next class.